fits nicely the theme of the conference. This is joint work with Liebke and Matsumoto, and everything is formal locally. So the setup is as follows. I'm working over an algebraically closed field, characteristic. Yeah. And for me, Rm, it's a local with theorem complete. Okay, algebra of dimension at least 2. It is just a fixed notation. X is spec R throughout the talk. Little x, I hope you can distinguish. It's the closed point. It's M. And then, okay, so these will be the singularities. When I say quotient singularity, I mean quotient singularity by a finite group scheme. Okay, so G is finite K group scheme. And Y will always be the power series ring. Okay, so what I want to do in this talk is first define what I mean by quotient singularity. So one possible definition of a quotient singularity, and then recall what is known about these quotient singularities over the complex numbers. Then I think there's no time to really discuss counterexamples in characteristic P, but essentially all the properties will fail in characteristic P. Okay, and then in the second part, I talk about one class of quotient singularities in characteristic P, the linearly reductive ones, where it turns out that everything works. And if there's a bit of time in the end, I'll talk about more general quotient singularities. Okay. So what is a quotient singularity? Okay, so for me, a quotient singularity is a quotient of Y by a very small action of a finite group scheme. Okay, and very small action is as follows: a G action rho on Y. It's called very small. Okay, so maybe you heard of the term small group action. Something about the fixed locus of the action. Okay, so what I want here is that rho is free outside the closed point of Y. Is it because I want to discuss, I forgot the word in the title, isolated quotient singularity. So one freeness outside of the closed point here. And one more weird condition, you want that rho fixes the closed point. Okay, and this comes from this generality here that we're talking about finite group schemes, not necessarily finite groups. Because of course, if you have a finite group acting on this Y has only one closed point, so of course you fix it. But if you have like infinitesimal group schemes, this is not automatic. Okay, so in other words, I want the fixed locus of the group action to be the closed point. The stabilizers outside the closed point are supposed to be trivial.
You see how it cannot fix? How it would not fix?
If G is not étal, basically, if G has an infinitesimal part, think of a vector field. You can move the closed point. Okay, so one thing that's like you have kxy, and you take a derivation dx. If P closed in characteristic P, it defines an alpha P action that moves a P closed point. Maybe I have to put 1 plus x here. Okay, there are these things. Okay, so we have okay, so an isolated quotient singularity. Okay, I dropped the word isolated. So for me, all quotient singularities are isolated. We call this QS. If there exists a G and a very small action. So G on X on Y.
It's very hard to see what you wrote. You know.
This is better. Yes. Thanks. So I want X, I call isolated quotient singularity if it's a quotient of policy is ring by a very small action of a finite group scheme. It's such that y and g is isomorphic to x. So really in over C, and for finite groups, it's just I want a finite group action on a disk, right? Fixing only the one point, free outside. Okay, so now I want to give you a list of properties of such quotient singularities over the complex numbers. Okay, so this is very old, very well-known stuff, but I want to recall it anyway. The properties of x, quotient of y by a very small action of C.
This is just invariant with something else.
It's just invariant. It's just GAT. Okay. So first observation is that since we're over C, this group scheme, as I said, it's étal, and it's the group scheme associated to a finite group. So we're really talking about quotients by finite group actions. Okay, so G is étal. And we're taking a quotient of this punctured y, basically, to get the puncture of x. So the fundamental group of the punctured x is exactly the group I'm modding out. So since x minus x is simply connected, this implies that if I take the fundamental group of the punctured thing, I take the group scheme associated to this, it's G. Okay, so the way I want to read this is I don't have to remember G. If I remember X, I can recover G.
Yes, X minus X is simply connected. I don't understand what you're saying. If you puncture X,
Y minus Y is simply connected, sorry. Oh, typo. Y minus 0 is simply connected. Yeah, thank you, thank you. Exactly. So I'm using here some kind of a purity for this power series ring. A purity for étal cover space. I'm saying this is simply connected. Okay, so I can recover Y as the universal cover of the puncture of X, and then taking a closure. Okay. And up until now, I'm just talking about these general group actions on the power series ring. And there's of course one nice class of group actions. They are given by linear group actions. Okay, so one important observation in this setting is that if you have a finite group over C and act on the power series ring, then this action is conjugate to a linear action. So we can forget about this extra generality. So by Cartan, Liberation, 1953, rho is conjugate to linear action. Okay, and again, the way to read this is without loss of generality. You can assume that G is in the GLD. Here we saw that we can recover the group, right? And now the question is, can you recover this group as a subgroup of the general linear group? And this is also true. This is due to 1967. The action is unique up to conjugation in GLD. Okay, so if I have isomorphic quotients, the groups are conjugate in this general linear group. Okay, I take two linear actions by the same group, isomorphic quotient, then they're conjugate. Okay, so this we can read as follows. It means that there's an injection from the set of conjugacy classes of finite very small on the set of quotient singularities.
Injection.
Okay, so now you can try to classify the singularities that arise in this way. But before I talk about this, let me talk a bit about birational geometry. So what kind of singularities do you get here? Turns out that you get KLT singularities. You don't get all KLT singularities usually. But at least you get KLT singularities. So X is KLT. I don't give a reference here. It's not hard to check. This is some ramification formula, and you compute with discrepancies. It's not hard. In particular, these singularities you get, they're always rational. They're the result of cyclic. These singularities you get are always rational. And your group is not just in a GLD, but in SLD. Then X is Gornstein. Okay, so you get certain isolated KLT singularities using this construction. And if you only look at subgroups of SLD, you get Gornstein KLT singularities. Okay, and then you can ask about the bijectivity of this map. Right, and it's classical over the complex numbers that this map here from finite very small subgroups of the general linear group of the conjugation is a bijection to KLT surface singularities. Okay, and let me write it like this. So if D is 2, then if I look at finite very small G inside SL2, I get exactly rational Gornstein X. Because I get exactly the rational double point. So this RDPs. AN, DN. Okay, this is very old. Okay, so this goes back at least to Klein, 1884. Complete classification of those finite very small subgroups of the special linear group of dimension 2 over the complex numbers, right? So you get a binary polyhedral group, and they are classified by these ADE Dinkin diagrams, and you can upgrade some of this bijection to really this correspondence. Okay, and then if we don't look at subgroups of SL2 but GL2, this is due to Brieskorn. You get exactly KLT surface singularities. This is due to Brieskorn. Okay, so this differs basically by cyclic groups. But you can also ask the same question in higher dimensions, right? You can still try to classify finite very small subgroups of the general linear group. It's maybe not as well known, but still classical. Those finite very small subgroups are completely classified. So this goes back to Klassenhaus, Vincent, and both. So there's a classification. Of finite very small groups in the GLD. 4D is 3. Okay, the motivation to study this is because there's a relation with what's called spherical space form problem. Namely, if you have a finite subgroup of this general linear group, and you have a this is very small, so the action is very small. Then you also have an induced action on the sphere of dimension 2D minus 1 without fixed points. Okay, and it's an interesting question to understand these kind of finite group actions without fixed points on the sphere. And the spherical space form problem is about the classification of these. Okay, so that was the motivation for this classification of finite very small subgroups. Here, let me maybe quickly summarize. Right, so we're talking about finite groups. Everything can be linearized. The group action is unique up to conjugation. We have some MMP properties for what kind of singularities we get as the image of this map here. In dimension 2, we got all the KLT singularities this way. In high dimension, it's not true, but we can classify the leptons. Okay, and you can also ask about deformations of these singularities. That's the last 2 points I want to make. This is also well understood. Okay, so this is the result of Schlesinger.
Sorry, can you use a different chalk?
It's 1971. Um,
Yeah.
So far, I only want Schlesinger. Okay, so if D is at least 3, then X is rigid. And even more, it's infinitesimally rigid. So there's no non-trivial deformations over Artinian local K algebras or isolated quotient singularities in dimension at least 3. And the last point is about deformations of surface quotient singularities. That's we need to write down deformations of these RDTs, for example, lots of deformations. But at least you can ask if given a quotient singularity, the deformation is also a quotient singularity. Okay, and this is Riemann-Schneider's conjecture. Was solved by Inu and Vivek. It was 1974. And Vivek proved this in 1983. Okay, so if P is 2, then there are deformations, but they're all quotient singularities. Okay, so this is the list of the complex numbers. Everything is nice. Talking about finite groups, we're talking about finite very small subgroups of the general linear group. Everything is well understood. We understand the singularities we get. We understand the deformations, and we can use the groups to describe the singularities. And now, so I downgraded this from a 60-minute talk that I gave before, and it had some examples that come now. I think there's no time to talk about these examples, so I want to summarize. So all of this fails. If P is bigger than 0, or CP actions already, for many things. Of course, the Italeness doesn't fail. And alpha P actions. Okay, so alpha P is the kernel of Frobenius on the additive group. And basically, the key problem is that this linearization fails. And this is the point I want to make next. Okay, so this is really an important part, this linearization. It turns out if you force the linearization of the very small action, then you don't have any problem. So this brings me to the second part, which is now about characteristic P, but it's a nice part of characteristic P. Basically, because what we do is we just exclude these bad guys. Turns out that everything works. So this is LRQ singularities. And let me recall, this LR stands for linearly reductive. It's a very nice class of group schemes and positive characteristic. They are defined as follows. So a finite group scheme is called linearly reductive. if every finite dimensional representation is semi-simple. Completely reducible. Again, the key example is the third type of group scheme of length p. So there's CP, there's alpha p, and there's mu p, and mu p is the standard example. The mu p is kernel of Frobenius on the other. Multiplicative. And I said everything, like all the issues disappear if you look at linearizable very small actions. And this I want to summarize in this following lemma. Turns out that if you have rho, a very small action, on y, then the following are equivalent. First, G is linearly reductive. Second, it's conjugate to a linear action. And more elementary, maybe, CP and alpha p are not in G. Somehow we're excluding the counterexample by the counterexamples we have here by force. And what we get is exactly linear reductive group schemes, and those are exactly the ones we can linearize. Okay, I can say a couple words about the proof, maybe. So 1 implies 2. It really comes from the definition of linear reductivity. Basically, you look at the action on the tangent space at the origin, and it has an equivariant splitting, which gives you a system of parameters with respect to which the action is linear. And proving that 1 implies 3, it's just a structure theory of finite groups. And 3 implies 1 also. Okay, and then if you have one of these acting on the power series ring by a linear action, and you have a representation of these groups are unipotent. So there's a fixed vector, and this fixed vector gives you a prediction with very small. Okay. So this class we get using these singularities. It's called linearly reductive quotient singularity. Let me write it briefly like this. X is called QS if it is QS by linearly reductive. And I want to spend the last 5 minutes writing down the list that corresponds to this classical list over the complex numbers. So what do we know about those linearly reductive quotient singularities in characteristic P? Assume X is linearly reductive quotient. Okay. Then first, there is a unique G by which X is a QS. Okay. And over the complex numbers, right, we use the fundamental group of the punctured spectrum. Here it's not enough because we also have quotients by this mu p. This mu p is not a tau. Well, induce a tau homeomorphism. So a fundamental group does not see this mu p. But we're claiming we can still reconstruct the group. And the way you do this is you say that G is well, it's a finite group scheme that splits into an epal part and a connected part. And this connected part is the Cartier dual of the p torsion of the class group. Okay, and this etal part. It's the etal fundamental group. of the function spectrum. Okay, so you can, as of the complex numbers, you can recover the étale part using a fundamental group. And turns out in the linearly reductive case, you can recover the connected part as the class group, and this should be some x bar, where x bar is the closure of the universal cover. So basically, you go up the étale part, you have something where the puncture is simply connected, and then the class group of this simply connected singularity gives you the rest, and then you have to say you can build back together your group scheme. So. And then just for completeness, unfortunately, this good chalk is very short, so I have to use this. Okay, thanks. Okay, so the second part is about linearization, right? And this G action can be linearized. So G action is conjugate to a linear action, this dilemma. So again, without loss of generality, we're talking about finite subgroup schemes of the general linear group scheme over the field. Okay, and any two G actions on Y with Y mod G isomorphic to X are conjugate. Okay, so this seems easy, but I think this is the hardest part of this theorem, because basically you have to, you have those two parts, and for this part it's tricky to prove that if you have a quotient by an infinitesimal linearly reductive group scheme, but any two actions that give isomorphic quotients are actually conjugate in the general linear group. Okay, so this is a bit tricky. Okay, but once we have this, we again get this nice map from finite very small subgroup schemes of general linear groups or special linear groups into singularities. But again, let me first say what kind of MMP singularities we get. We get that X is strongly F regular. Okay, so in particular, this implies KLT. It implies rational. Okay, but it's stronger, at least in small characteristics or high dimension. And so we get these kind of singularities, just some kind of nice singularity in characteristic P. And let me write maybe what. So this is one of our main results, but this part 4 was known. And I just put the list here, so you're able to compare it with complex numbers. So host to Unica is known. Basically, because if you take this invariant ring, then the inclusion into Y, it splits. And so you have a direct summand of a regular ring. Okay, and again, if G is an SLD, then X is constant. Okay, now we do the same thing as on this right part. We ask in dimension 2, what kind of singularities do we get? Turns out we get exactly the strongly at regular surface singularities. Okay, so A, we look at finite very small. P in SL2 up to conjugation. We get 1-to-1 F regular and P is at least 7 every rational double point is F regular. So in characteristic at least 7, you get exactly the same correspondences over the complex numbers, except that on the left you have to allow infinitesimal group schemes. If you only look at étale ones, this is not true. So you get RDPs. And the same in the GL2 up to conjugation. Okay, I just want to finish this list. So as you can imagine, there's 3 more points and then
Sorry, could you say again, what is F regular?
strongly F regular. So I don't want to define something about splitting maps that look like Frobenius. But you have to also, okay, I don't want to define it. Some notion of singularity that's nice in characteristic P. So what you get here is F regular surface singularities. So every surface singularity that is F regular is a quotient singularity by a linearly reductive group scheme. And again, if I do not define what F regular is, if the characteristic is at least 7, those are exactly KLT singularities. So in characteristic at least 7, every KLT singularity of a surface is a quotient singularity by a linearly reductive group. Again, here it's 5A is due to Hashimoto and Liedtke-Satriano. And 5B is C. Okay, so as I said, there are 3 more points. Okay, 6th point is classification in higher dimension. As you see here. Turns out this is not too hard if you know the complete classification over the complex numbers. So there's a classification of all finite, very small in GLD and SLD. Okay, so in other words, we know exactly all linearly reductive quotient singularities that are isolated in all dimensions. So we have a complete classification of all these. And there's a way to read this off from classification over the complex numbers. Usually it's different over the complex numbers. It's a bit smaller.
It's fail for nonlinear.
So the big problem is that, so I'm writing here only finite very small and never linearly reductive, right? Because the very small ones in the general linear group, they're always linearly reductive. Okay, so in that sense, it fails because they're not even subgroups of FGLT. So I want to classify the quotient singularities by very small actions of more general group schemes. I have to look at very complicated actions. Yeah, okay. So it's going to be very quick. Just do like 7, 8. So you can ask for rigidity. If P is at least 3, when X is rigid. And if D is at least 4, then X is infinitesimally rigid. So there's something interesting happening here, a remark I want to make. I omit the infinitesimal here because it's not true in dimension space. That are quotient singularities that are rigid, but not infinitesimally rigid. This is interesting. And if D is 2, then X deforms reductive quotient singularity. Okay, so this is the analog of Riemann-Schneider's conjecture in characteristic P, and this is due to Sato Takagi. And we proved this in the Q-Gorenstein, in the case of Q-Gorenstein deformations, where it's not hard. But if you drop this assumption on the total space, it's much harder. And this is proved by Sato Takagi. Okay, and then there's much more you can say about non-linearly reductive quotient singularities, and we had some questions, but I should stop. Okay, thanks.